Hello, welcome. In this video we are going to state and prove a necessary and sufficient condition for a family B, a family script B of subsets of a topological space X to become a basis for some topology of a topological space X. So the see, this is the complete statement. A family B of subsets of a topological space X is a basis for some topology of X if and only if both of the following conditions hold. Condition 1: the union of the members of script B is X. Union of the members of script B is X. And the second condition is for each members, pair of members B1 and B2. See, for each pair of members B1 and B2 in script B, and a particular element X in the intersection of the pair of members, that's X belonging to X is an element of B1 intersection B2. There is a member Bx of B of script B. There exists another member. There exists one more member Bx of B indexed with X, Bx of B, such that X is a member of Bx, is a subset of B1 intersection B2. So these are the two conditions that need be satisfied for a family B of subsets of X to become a basis for some topology of X. Let's see the proof. First, we suppose that to prove this this necessary and sufficient condition, first of all, we suppose that script B is a basis for the topology of X. By the definition of the basis, see, the definition of the basis says that every open set in the topology can be written as the union of some member of script B. If script B is a basis, see, the definition of should recall the definition of the basis of a topology. By the definition of the basis of the topology, every open set in the topology, see, we know that topology contains open sets. Topology is a collection of open sets. So every member of the topology, so see, every member of the topology or every open set in the topology can be written as the union of some members of script B. So that is the by definition, this is the condition that must be satisfied by this collection of subsets of X to become a basis. The entire space is so. Thus, in this sense, we can see that the entire space is a member of the topology. Since the entire space, that is X here, X is the entire space. Since X is a member of the topology, whatever topology it is, X is a member. The full space is a member of the topology. Yeah, that we can write X is here. We symbolically it is written as X. X is an element of the topology. Then, due to that reason, due to the definition here stated, we can say that X can be written as the union of some members. See, X is equal to union of B, where B is a particular member, a typical member of the script B. So union of B, there exists some members of script B, such that their union becomes X. Thus, A part is proved. Then to prove B, we take two members B1 and B2. Let's consider two members B1 and B2 of script B, and an element X of the intersection of the two members So we also consider the intersection of B1 and B2, and X is a member of that intersection. Since B1 and B2 are open sets, we know that B1 and B2 are open sets because they are members of a basis. Because they are open, so they are open sets. B1 and B2 are also members of the tau. Both elements, both these sets are members of tau also. And so in their intersection, B1 intersection B2, what about that? About their intersection, that's also a member of tau, because that's open intersection of any two open sets is also open. So B1 intersection B2 is also an element of tau. Since B1 intersection B2 is open, there exists a subset. There exists a set of members of B such that, see, since B1 intersection B2, their intersection is open, then there exists, by applying the definition of the basis, we can say that there exists a set of members of a script B such that its union equal to B1 intersection B2. Yes. Then we can since it's the union, since the union can be written, union of B1 and B2 can be written as the intersection of the open sets B1 and B2. B1 intersection B2 can be written as the union of some members of B, and also since the element X, that particular point X belongs to the intersection, then there must be one member of script B, one member of this collection script B that contains that particular element X. It's because X is a member of this intersection. X is an element of this intersection, and also there exists a collection of open sets which are members of script B, whose union is equal to the intersection of B1 and B2. Thus, it is clear that there must exist at least one open set. There must exist at least one member of B open set, that's a member of script B, which contains that particular point X, which belongs to this intersection. So that particular member of script B can be chosen as it can be named as Bx, and that is selected. That can be taken, and we can now we can write that X is an element of Bx. Clearly, X is an element of Bx, and that's a subset of B1 intersection B2. So proof in one direction is now complete. Now to prove the to prove the result in the reverse direction, the opposite direction, we suppose that a collection of open sets script B is there exists, or it's taken, and we suppose that there exists a collection of open sets script B which satisfies the two conditions A and B, or two properties. This collection script B satisfies the two properties A, and the property A and the property B. And then we want to show that there exists a topology tau such that B is a basis of that topology. See what we want to show now, and we want to show that there exists a topology. There exists a topology tau such that script B is a basis of that topology. How can we show there exists a topology? For this, we want to define a topology first, and then we will show that it's actually a topology. So there are two things to be done. First, we want to define, or we want to show that, we want to argue that there exists a non-empty set. There exists a family of subsets of the topological space X, and that family actually acts as a topology. That means that contains open sets, and it satisfies all the axioms, all the three axioms of the of topology. So we define. First of all, we define the tau. tau is defined as the set of all possible union of members of script B, and this way we define tau. How do we define tau? Tau is defined that family or the collection of open sets is defined as the set of all possible union of members of script B. And after defining that, we want to show that tau is, or this collection, this defined collection is actually a topology for X. So that is the second thing. What is the second thing we want to show? The second thing we want to show that this collection which is defined here, and that is defined as the set of all possible union of members of script B. And script B is a given collection of open sets. Open subsets of the topological subset of the topological space X. Then how can we show that it's a topology? This that collection defined here is a topology. We can show one by one all the three axioms are satisfied. So let's consider the first axiom 1. Axiom 1. Here we want to show that X belongs to tau. Also the null set belongs to tau. X belongs to tau because of the condition A, because of the first condition which is accepted here as true, that says that the condition, what is the condition? That the condition is that or the statement, the first statement is that X can be written as the union of members of X can be written as the union of members of script B. So that is the first property or first condition. Therefore, due to that, X can be written as the union of members of X can be written as the union of members of the script B, and since we have defined that tau contains the set of all tau can contain the set of all possible union of members of B, what happens, and that X then as a consequence of this accepted statement, X becomes a member of tau. And next, to show that the null set is a member of tau, we accept that reason that it's because of the fact that phi is the union of an empty collection of members of script B. See, here we can consider an empty collection. An empty collection means there is no element in, or there is no member actually present in that collection, and that empty collection can be taken to make the union. Then we can see that union will not contain any of the elements of X, and thus it's the null set. So null set is also a member of tau. Next, to show that the condition 2 of the topological space, or the axiom 2 is satisfied. We want to show that axiom 2 of the topology, is satisfied. For that, we have to consider any union of members of tau. So here we take an arbitrary union of members of tau. We have to consider an arbitrary collection of members of tau, and then we will take its union. So that means we want to show that any union of members of tau is again in tau. So for that, let us consider the members O1, O2, O3. We name them V1, O2, O1, O2, O3, etc., OM, then etc. It goes like that. It continuously we have to choose open sets. And all these open sets are members of tau. So we choose these members or these elements from the topology tau. We cannot call it topology now. We can call it only a collection. That collection is defined here. So from the collection which is defined here, the tau is the collection which is defined, which is stated here, and that from that collection we choose the members, an arbitrary union, arbitrary collection of members is chosen. So arbitrary collection means it can contain only finite or infinite. Some cases it can contain finite number of subsets. In some cases it can contain infinitely many members of tau. Then what we do, we have to find its union. We take its union. We take the union. We also know that each OI is for each of these members chosen. We can see that each of them is the union of some members of script B. See, after choosing O1, O2, O3, etc. OM, then like that we choose many members, and then we can see that each of these members, each of these open set is a union of some members of script B. Why? It's because these are chosen from tau, and tau is defined in this way. So tau is defined in such a way that each of these members is the union of some members of script B. So using the definition of tau, you can state it as given here. Then you can that means OI is equal to there exists then members of script B. These members are BI1, so corresponding to OI, with there exists members BI1, BI2, BI3, etc. BINI. Suppose that there these are the members that exist in script B. So BI1, BI2, BI3, etc. to BIN, and then by taking its union you can obtain OI. Then OI equals BI1 union BI2 union, etc. union BINI. And then we consider the union of all these selected members of tau, O1 union, O2 union, O3 union, etc. That can be written. Then in each case you can replace by each of these member can be replaced by the corresponding union. There exists a corresponding union for O1, there exists a union for O2 using the members of all these are using the members of script B. So we can write that O1 equal to B11 union B12 union, etc. B1 and B1 N1, and then O2 is the union of a similar collection. Those members are B21 union, B22 union, etc. B2 N2, and then continuing each of these members can be, each of these open set can be written, and that in this in this way you can write. So in this form you can write all these members. So now you can see that it's a very big a string of members of script B. Thus, and also we can combine all these unions, because we are taking operation union inside each bracket, and outside the bracket also the union operation is used. So you can combine these unions. All these unions can be combined, and you can take them as a single union, and that means the union of O1, O2, O3, etc. to ON, etc. is a union of members of script B. And that means this is a member of a thus it makes, see, this expression actually makes the left hand side expression eligible to be treated as a member of tau, because we can by definition of tau we can say that all members of tau are the union of some members of script B. So thus it is here it is clear that this union can be the left hand side union, which is written on the left hand side, can be written as the union of members of script B. So this union is a member of tau. Then next we proceed to prove the axiom 3. In axiom 3 we consider we have to find the finite intersection of members of tau. So we want to analyze the nature of the finite intersection of members of tau. Okay, that must also be this finite intersection must we want to show that a finite intersection of members of tau is again a member of tau. So okay, that first we for that we consider two open sets into. So we will do it in a step by step manner. See, first we consider two open sets into and yeah, these open sets are O1 and O2. We take these two open sets O1 and O2. Next we shall show that O1 intersection O2 is again is present in tau. So O1 intersection O2 that intersection is now taken here, and you can think about a member of that intersection. See, we consider O1 intersection O2. Actually, we want to show that O1 intersection O2 is a member of tau. For that, when we consider O1 intersection O2 and a member of and a point of the intersection, and let X be a point of the intersection O1 intersection O2, since X is then X is clearly is present in O1. Since X is present in O1 and B is a basis for tau, since B is a basis for tau, there exists B1 in B, such that X is an element of B1 and B1 is a subset of O1. Yeah, then that's this is obtained by using the definition of basis. See, since X is a member of O1 and B is B is a basis for tau, there exists a member of the basis, that's B1 is a member of the basis, such that X is an element of B1 is a subset of O1. So this can be applied. The same argument can be applied in the case of O2. Because since X is an element of O2, similarly, since X is an element of O2 and B2 is there exists B2, maybe some different member of B, script B, that is here taken B2. That element is named here as B2. A member of script B says that X is an element of B2 and it's a subset of O2. Therefore, X is an element of B1. Thus, clearly X is an element of B1 intersection B2, because X is present in B1 and B2 at the same time. So, X is an element of B1 intersection B2, but B1 intersection B2 is a subset of O1 intersection O2. That is very clear. And thus, now by the second statement, see. And this is now once again X is a member of we state this, that how do we get it? X is an element of B1 intersection B2 and it's a subset of O1 intersection O2. See, the steps used to show this is given here. Now, by the second statement, see, since we have accepted second statement is satisfied by script B, or second statement is true for script B, for the members of script B, there exists Bx. Then, since X is an element of B1 intersection B2, there exists Bx in script B. Applying that statement, second statement, there exists, we can say that there exists Bx in script B such that X is an element of Bx is a subset of B1 intersection B2. So Bx is a subset of clearly Bx is a subset of, again using, once again referring this, since this intersection is a subset of O1 intersection O2, it is clear that Bx is a subset of O1 intersection O2. And therefore O1 intersection O2 can be written as the union of members of B. Thus it is clear that since Bx, there exists Bx in script B, such that Bx is a subset of O1 intersection O2, you can now you can say that O1 intersection O2 thus clearly can be written as the union of members of B. There are thus see okay. Then we can extend it to the extend the same argument can be extended to 3 open sets, open sets in tau, or 3 members of tau. So for that we take O1, O2 and O3, 2 members of tau. We want to verify it in whether it is true. In that case, all the statements or all the arguments that we have given just above, whether these arguments are valuable or correct for the 3 members of 3 elements of tau. So first, O1 intersection O2. First we consider the 2 members, first 2 members, O1 and O2 and their intersection. So O1 intersection O2, and we know that using the previous argument, O1 intersection O2 is a member of tau. That's thus it's an open set. Thus we can take them together. O1 intersection O2 can be taken as one element, one member of tau, and then the third member is also third element is chosen, is used. Thus we can reduce it to the case of 2 open sets. See, this is now very similar to the arguments that we have given above in the case of 2 open sets. Okay, and therefore we can say that the intersection O1 intersection O2 intersection O1 intersection O2 then intersection O3, that is the intersection of the 3 members O1 intersection O2 intersection O3 is in tau, and this can be extended to the case of n open sets. See, in the case of n open sets, we can say that this is extendable, and the argument is extendable without any doubt. We can say that the union of after extending all the arguments to without any fail, we can extend it to the collection of n open sets which all belonging to tau. Then we can say that the intersection of this finite union is also an open set, and that belongs to tau. So we can say that the third axiom is also verified. So that means there exists a topology, and that topology tau is very well defined. It is very clearly defined at the beginning of the revised conveys part of the proof. We can see that that collection acts as a topology for X. Thus there exists that the collection which satisfy any the collection of open sets which satisfy the condition A and B can actually create a topology for X. Okay, that is the end of the proof. Thank you for listening.